Alright, Assalamualaikum and good day to all. So we will continue with the last learning unit, which is analytical separation technique. So this would be the learning objectives for this learning unit. So the first learning objective would be describe and explain general principles and theory of analytical separation. Okay, secondly, describe and explain different analytical separation methods. Thirdly, the calculation part, which is solving retention factor of individual component in mixture of colored compounds. So what is separation? Okay, separation means we are isolating the analyte of interest from potentially interfering constituents so that we can do quantitative analysis. So the basic principle of separation is either complete or partial. Okay, so let's say you want to identify each and every component in a mixture, for example in this figure here. Okay, you can do separate separation, so each component are separated, okay, completely. Now if you only focus on one analyte of interest, or you want to find only one component in the mixture, you can do partial separation. Okay, partial separation because you only want to find out about this analyte of interest. Okay, the rest it's okay if they're in mixture. Okay, so you can do partial separation. Okay, so these are the different type of separation methods. Okay, depending on the analyte that is going to be separated from its mixture. The first type is chemical or electrolytic precipitation. So some analyte of interest can be separated from mixture or from solution through precipitation, like what you have covered in learning unit 3. So your analyte of interest is precipitated out, okay, from its solution. The next type is distillation, and then solvent extraction, ion exchange, and chromatography. So these four will be covered in this learning unit, so we will look at this later on. The next two, electrophoresis and flow fractionation, is more advanced, so we will not cover this in this learning unit and this course. Okay, but a glimpse of idea what electrophoresis is. This is actually a technique that is used to separate charged molecule. So if molecule have charge, for example like DNA, so they can be separated. Okay, and then they are separated based on their different in size. The next one, flow fractionation. This one is separation based on size or mass when the sample component are being flow in a channel or in tube. So let's say you have this channel or this tube here, and this is the mobile liquid that carries along the analyte of interest, and then field is being applied in the perpendicular direction, and the component here will be separated based on their different size or mass. So if bigger size, they will move slower compared to smaller mass and lighter. Okay, so they are separated there. Okay, here we will look at different classification of separation technique. Okay, let's say if you want to separate based on size, these are the technique that you can use. If you want to separate based on the mass and density, the technique will be centrifugation. Okay, for example, size filtration, you did it in practical class. You separate suspended solid and dissolved solid, so you do using filter paper. Okay, if you want to separate based on mass and density, we can centrifuge. So you can centrifuge blood, so that you can obtain the different component of blood, which is RNA, DNA, and so on. So they will be separated based on different in density and as well as mass. The next type of separation is complex formation. The technique used is masking. So remember when you study learning unit 3 on precipitation, so you don't want any interference to precipitate along with your analyte of interest, so you mask, okay, the interference, okay. So it will form complex, and you can filter that out first, and then you proceed with the precipitation of your analyte of interest. The next basis of separation is change in physical state. So change in physical state, the technique involve either distillation or recrystallization. So this also you have covered in learning unit 3. Okay, so you want to get pure crystal, so you dissolve and let it crystallize out again, so that you get pure crystal or pure precipitate. Distillation will be covered next. If you want to separate based on chemical state, then precipitation will be one of the technique that can be used. Ion exchange, electrode deposition, or volatilization. We will look at ion exchange and volatilization later on. Okay, so precipitation is one of them and has been covered in learning unit 3. You change the chemical from let's say silver nitrate is the aqueous solution, it become silver chloride. Okay, so you change your chemical state from silver nitrate to silver chloride solid, okay, after precipitation process. The last basis of separation is based on the partitioning between phases. The technique that can be used is either extraction or chromatography, so we'll look at this later on. Okay, and those in box here are the method based on mechanical phase separation. Okay, so the first mechanical phase separation is separation based on change of state. Okay, so change of state means from liquid to gas, gas to solid, and so on. Okay, so you have 3 different states: gas, liquid, solid. So one of the technique is distillation. Okay, so there are 2 type of distillation. Either we can use simple distillation or fractional distillation, and this fractional distillation is more efficient because it will distill every component in the mixture. Okay, simple distillation is separating liquid if they have large difference in terms of their boiling point. Okay, so this is simple distillation technique. Let's say you have prepared sodium chloride solution. Okay, awak ambil garam dapur tu, awak letak dalam air, awak dissolve dia. So can you obtain back the salt? Okay, boleh dapat balik tak garam tu? Yes, you can. Okay, when you apply a simple distillation technique like this. So this is the setup. So you must have water inlet and water outlet. Okay, this one has to be continuous. Okay, so awak pasang benda ni dekat pipe, make sure air sentiasa mengalir. Alright, because once this boil and form vapor and it go through this condenser here, it will cool down. When it cool down, it will form back liquid form. Okay, so you will collect your water here, and in the end what is left here is salt only. Okay, setelah semua air tu dah vaporize. Okay, make sure it boils. Okay, at boiling temperature of water. Okay, so you can watch this video here. Okay, on simple setup of distillation technique. This is example of fractional distillation. So this is a more complicated setup. Okay, this is a simple distillation. For example, crude oil. Okay, ini yang orang dekat tengah-tengah laut tu. Okay, orang Shell ke Petronas ke, okay, cari gali. So they obtain the crude oil. Okay, the crude oil is a mixture of many components, and what we want is probably one of the component. So how to separate the crude oil into its component? So it undergo fractional distillation. Okay, fractional. Okay, so at lower temperature, gas can be collected. Okay, and then at slightly higher temperature, not slightly, at 150 degrees Celsius, okay, we can collect gasoline or petrol. The rest is still remain as mixture. But if we increase the temperature higher, up to 200 degrees Celsius, we can collect kerosene. Okay, further high in temperature, up to 300 degrees Celsius, we can obtain diesel oil. Okay, and at 370 degrees Celsius, fuel oil. Okay, and then lastly, at 400 degrees Celsius is the remaining lubricating oil, paraffin wax, and so on. Okay, and these are the components that are very useful to different type of vehicles. So the next technique is recrystallization. Okay, so we have covered distillation. So we look at recrystallization. So this is a technique where we only apply minimum volume of solvent. Okay, and the analyte solubility will be very high when the solvent is hot, and the solubility will be low when the solvent is cold. Okay, so this is very useful if you want to do we want to obtain pure crystal or pure analyte of interest in form of precipitate. Okay, so let's say the precipitate obtained having impurities also. So what we can do is recrystallization. That precipitate we redissolve. Okay, redissolve in solvent. Okay, gradually heating up the solvent so that all the precipitate will soluble. Okay, solubilized inside the solvent, and then slowly the solvent is cooled down. During the process of cooling down, okay, the precipitate will come out as pure, and the interferent will remain in the solvent. Okay, so this is recrystallization. Okay, the second type of mechanical phase separation is separation based on partitioning between phase. So it has to involve analyte, okay, between two immiscible phase. Means you must have two phase which is immiscible with each other. For example, oil and water, so they are immiscible. Okay, so for the solute or the analyte of interest, okay, in contact with a second phase, okay, the solute will partition between the two phase 1 and phase 2. Let's say you have analyte of interest in one of the phase. Okay, how much of the analyte of interest, okay, in this phase here, phase 1, partition into phase 2. Okay, and this at equilibrium is calculated based on the distribution constant K. Okay, K subscript D is the distribution constant, and the square root is the square bracket here represent concentration. So concentration of solute, okay, analyte of interest in phase 2, and concentration of solute in phase 1. So if your KD value is large, okay, if this value is high, okay, big, means the solute move from phase 1 to phase 2. Okay, it move from phase 1 to phase 2. Okay, so from 1 to 2. So higher concentration of the solute in phase 2. So that's why this one is large. If KD is small, if this value is small, okay, means solute remain in phase 1, or it partition very little to phase 2. Okay, so separation is possible when KD favor for only one of the solute. Okay, so you have to select a good solvent for the analyte of interest to partition to. Okay, otherwise you will not get a good KD value. Okay, next we will look at separation by solvent extraction. So we have covered the mechanical. Now we look at solvent extraction. So this extraction will include either liquid-liquid extraction, liquid-solid extraction, solid-liquid extraction, or gas-liquid extraction. So we will look in detail each and every type of this extraction. Okay, the first one is liquid-liquid extraction. So the glassware used for liquid-liquid extraction would be separatory funnel. So this is how separatory funnel look like. It look more or less, the principle is like burette. So you have you can control the water, okay, water out from here, okay, and then you fill in phase 1 and phase 2 through here, and then you close it, okay, with the stopcock here. For example, we want to quantify pesticide in water. So pesticide is soluble in water. So how to quantify this pesticide? We can extract the pesticide into hexane. So phase 2 would be our solvent here, which is hexane. Okay, and then we shake this phase 1 and phase 2 together. Okay, why we shake? Because we want to increase the surface area between the two phase, so that we allow the pesticide in phase 1, the aqueous phase, water, to partition into phase 2. Okay, remember we want our KD to be high. Okay, so after shaking, we drain out the aqueous phase, okay, and then followed by phase 2 into a different beaker, and then this solvent can be volatilized, or we when it volatilized, what remain behind is pesticide. So we can, then you can weigh the pesticide into that partition into phase 2, or the organic phase. Now the disadvantage of this type of liquid extraction, it only limit to those that are water immiscible. Okay, the solvent here, okay, must be immiscible. Okay, that's why you must have two different phase. If it miscible, then the extraction wouldn't be successful. So this is the formula, okay, involved in liquid extraction. Okay, so the solute will partition between two immiscible phase. Okay, usually one phase is aqueous, one is organic solvent. Okay, so if the solute initially in aqueous phase, okay, this is aqueous phase, and extracted into the organic phase, the partition coefficient would be this. Okay, to know the efficiency of extraction, okay, whether it's 100% efficient or not, okay, we need to know the distribution ratio, okay, D, which is the ratio of the solute total concentration in the organic phase and also the solute total concentration in aqueous phase, okay, and this distribution ratio D is then substituted, okay, the D distribution ratio value and then substituted in this formula to find the percentage of efficiency, okay, of the liquid extraction, okay. V here is the volume used in the extraction process. O is the solvent, okay. A is the aqueous phase, okay. Please take note that this formula here can only be used for single extraction only. So if you do more than one extraction, then you cannot use this formula, okay. So more than one, you have to use this formula instead, okay, to calculate the percentage of efficiency. The best thing is this formula can be applied for both single extraction or multiple extraction. So I suggest you memorize only this formula because it applies to both, okay, both cases. So this is the calculation for efficiency, okay. 1 minus the concentration of ion, okay, remaining in aqueous layer over the original concentration. Sorry about the typing. Yeah, it should be concentration, okay, remaining in aqueous layer, okay, of the solid. Okay, to find the concentration here, okay, we use this formula here, okay. So V is the volume of aqueous, D is distribution ratio, this one is volume of organic, this is how many extraction that has been done, this is the original concentration, okay. If concentration is not given but mass instead in gram, then you substitute this using gram. So this remaining, okay, will be in gram also, okay. To understand better, this is example of liquid extraction. So you have 1 gram of solute dissolved in 100 ml of aqueous solution, okay. Calculate the amount of solute remaining in aqueous phase after a single extraction using 90 ml of solvent, a single extraction using only 30 ml of solvent, or we do 3 successive extraction using 30 ml solvent. And distribution coefficient is given here, 10, okay. So value of D here is 10. So how to calculate A, B and C? You have to use the formula involving you have to use the formula given in the previous slide, okay, to find what is remaining, okay, amount remaining. Remember, it is in square bracket, means concentration, okay. So here it is given in the form of mass, which is 1 gram, so the final answer is also in mass. So substitute it in the formula for A, B and C. Initial mass is 1 gram, okay. 100 is the volume of the aqueous phase, okay, and then distribution ratio is given 10, okay, 10 times volume of solvent plus volume of aqueous, okay. So this is single extraction, 3 successive extraction, so 3 here, 4 successive extraction, so 4, if 5 excessive extraction, then 5, okay. So you have to do this first, okay. D times the volume of organic, then you add with the volume of aqueous, okay. So this is the remaining of solute, okay, in the aqueous phase after partition into solvent phase. So you see here, using large amount of volume of solvent, 90 ml, only about 0.1 gram of solute remain. But if you only use small volume, which is only 30 ml of solvent just now, quite a lot of the solid remain behind in the aqueous phase, which is 0.25 gram. But if you do more than one successive extraction, for example in this case 3, and each extraction we use 30 ml, okay, so this one remain behind. So rather than using 90 ml straight away, we divide into 3 portion of 30 ml, and then we do extraction. So only 0.0156 remain behind. So how to calculate the efficiency of extraction? Okay, we use the following formula after that. Okay, 1 minus the concentration remain over the original concentration times by 100. Okay, so like I mentioned just now, the second formula is can be used for both single and also multiple extraction. So memorize that formula instead. Okay, so the first one 90% efficiency, second one 75% efficiency, and third one is 98.4% efficiency. So the third one, C, is more efficient. Okay, more efficient to obtain for the solute to be partitioned into the solvent. Now the second type of extraction is liquid solid. Okay, so the first name here, liquid, imply the sample. So liquid is the sample, solid would be the adsorbent in this case. Okay, so we have a cartridge here. Okay, so this cartridge is packed with a solid adsorbent. Okay, and then this would be the flow of the sample. So it will pass through the solid adsorbent and come out at one end here. Okay, for example, we can isolate sedative from serum. Okay, so you have serum and that serum have sedative, and you want only the sedative, so you can isolate that using a carbon 18 solid adsorbent. Okay, so the sedative is retained. Okay, retained, and the remaining of the serum will pass through. Okay, then we pour in solvent, which is acetone, so it can elute out the adsorbed sedative, okay, out here, and then you collect it. Okay, the advantage of this liquid solid extraction, very easy to use. Okay, faster extraction time, and we don't need much of solvent. Okay, smaller volume, and you can concentrate the analyte. So the next type of extraction is solid liquid. So based on the name, the sample is in solid form. So the solid sample is placed inside a porous cellulose filter thimble here. So it's open at one end here, and then in the lower reservoir, solvent is being placed. Okay, and then it is vaporized at its boiling temperature. So we put this lower reservoir on a hot plate, and then the solvent will vaporize, okay, and go here. Okay, and because there's a condenser here where there's water inlet and outlet, the vaporized solvent will cool down and drop inside this thimble here, okay, as liquid form. Okay, until at one point, it flooded the sample here. Okay, and then the sample will extract out into the solvent, and then it return back from this return tube into the reservoir, and this process is continuous until in the end the analyte of interest is collected here. Okay, collected here. So this is a solid liquid extraction. This is chocolate extractor setup. Okay, the advantage of solid extraction technique, it only use small amount of solvent because it's being recycled. Okay, collected back in reservoir and then boil back and then collected back. Okay, so only small amount is needed. Okay, and it can remove a high percentage of solute. Okay, and you just can leave this chocolate extractor unattended for a long period, because normally it would need at least 8 hours. Okay, the water has to be continuously supplied, okay, in and out. Okay, the next type of extraction is gas liquid. Okay, this is the setup for gas liquid extraction. Okay, so this is where the sample inlet. Okay, and then the sample is converted into vapor and then collected here. Okay, vapor outlet, and then the liquid outlet, okay, will be flowed here. Okay, so example here, example of gas liquid extraction is mercury. Okay, and mercury can be isolated from liquid sample. For example, in this case we use seawater. So we take seawater sample and we only want to obtain the mercury inside the seawater. Okay, so we use argon gas. This argon gas is heated so that the mercury will be separated from the seawater. Okay, by changing that mercury in the form of liquid, okay, soluble liquid in seawater, into mercury vapor, okay, in the separation chamber. Okay, and then this liquid then flush away to the waste container. Okay, the advantage of using gas liquid extraction is very easy to use and very fast extraction time.